So this is a problem. We're given two sorted arrays of arbitrary lengths, and we want to find the median of their union. So say that one of the first arrays A and the second array is B. The union of both of these arrays, we get 1, 2, 3, 4, 5, 6, 7, 8, 9. And the median will be 5 because 5 is the middle of this array. And the reason for it is because 5 has 4 numbers smaller than it and 5 numbers bigger than it. So by definition, what median means is that we have 50% of the numbers in the list bigger than the median and 50% of the numbers in the list smaller than the median. So that seems pretty straightforward, right? So pretty much all we want to do is get the number in the middle. So one way to think about this is, given an array, just picks the number in the middle of its sorted. So if A is equal to 1, 2, 3, and we want to find the median of A, it's just 2. But let's consider example number 2. What if A is now 1, 2, 3, 4? It doesn't really have an exact median because it's an even number array, right? So what we actually do in this case, if the array is even, we take the average of the two middle numbers, then return that. So in this case, the median would be equal to 2 plus 3 divided by 2, right? And it's equal to 2.5. So 2.5 would be the median because this array is even lengths. So now that we know this, maybe we can come up with a solution to solve this problem. So we can come up with a few approaches. So maybe why don't I just make a class called let's come up with the first approach, approach 1. So we're given two arrays, right? And we know that they're both sorted. So maybe we can do something like we can make an array C that is a union of A and B that's sorted. So approach 1 could be make a third array that is the union of A and B in sorted order. So maybe we can do something like this. C goes to A plus B and C that's sorted. Right. So we combine A and B into C and we sort C. And now we can find the length of C. So n equals to length of C. If n modulo 2 is equal to 0, so if the union of the two arrays are even, then we need to take the average of the two middle numbers, right? So we can say something like return C of n modulo 2 minus 1 plus C of n divided by 2.0. Or if it's so, it's even. If n is odd, then we can just return C of n modulo 2, right? So this is a pretty simple solution, and it's not very difficult to come up with because we looked at the definition of what the median is, and we drew up a simple example where we just literally combined A and B and then put in sorted order and then just directly access the middle element because we take advantage of the fact that the union of A and B are sorted. So the main downside of this is that we have to sort the array. So the running time of this algorithm would be n log n, where n is equal to the lengths of the A and B, and space would be log of n. So for approach 1, the big old running time would be, let's say, A equals to length of A and B is equal to length of B. So that means the big old running time is and let's say n is equal to na plus nb equal to O of n log n in time and O of log n in space. So this is not bad. This is something that you can come up with quite fast. And the main thing that we really have to care about here is whether or not n is even or odd. So this is a pretty simple solution. Now your interviewer might be saying, your array A and B is already sorted. You're kind of doing a lot of work by sorting it again in line 26. So is there a way to get the median without having to sort your array? And you think to yourself, oh, well, you're merging the two arrays to get their union. So instead of sorting them again, maybe we can think of something that we already know. And what we know is merge sort. In merge sort, we can sort two sorted arrays in order of n plus m time, where n and n are the lengths of the arrays respectively. So this is an approach that we learned in divide and conquer, the merge sort. So maybe we can try that. So let's try def approach 2. So A and B. C is equal to self.merge of A and B. Def merge B. And then we do the same thing as we did in approach 1. But now, how do we actually implement the merge algorithm so that it takes order of NA plus NB order in time? Because this is much faster than approach 1 because we are saving a log n factor. So if you remember in merge sort, we can do something like this, naively implemented. If not A or not, if not A or not B, return A or B. So what this line means that if one of the arrays is not is empty, return the full one. Else if A of 0 is less than B of 0, return 0 plus self.merge B, right, else right, we break the array down, we break A and B down one by one and compare the first number in each array. So to give a more concrete example, let's look at A and B. So merge will compare the first element in A and B. So we see that B is smaller than A. Then we would put 1 in the beginning. And now we pass this into the next merge. And now we compare 2 and 3. 2 is bigger. So now we pass 5 and 7 and 3 and 4. And now you'll say 3 is bigger than 5, so 3 will come next, etc., until we finish going through one of the arrays. But this is actually naively implemented. This takes more than of NA plus NB time because of line 43 and 45, because this is not implemented properly. When we're doing list slicing, even though it's very simple, very intuitive, this line actually takes the order of n time because we're passing a copy of this array. So don't do list slicing because it increases the time complexity. So what we do instead is, instead of using list slicing, we pass indices of A and B. And I'm going to say I is equal to index of A, and J is equal to index of B. Index of B. So how do we actually rewrite this whole merge function? So the first index that we pass is just the first index, right? Because we the 0th index. So what we care about initially is the first element in each array and see who is bigger than who. Okay, so let's do that. But what happens if we get to the end or if the list is empty? Like, how do we then rewrite line 43 to 44? Well, it's quite simple. We can do something like this. If I is greater than or equal to len of a, that means we're out of bounds or the list is empty. Then we can just simply return b of j, whatever b is. Now if j is greater than or equal to len of b, return whatever is left in a, right? If a is empty or there's nothing left in a, return whatever is left in b. Likewise, if b is empty or there's nothing left to compare in b, just return whatever's left in a. So this is our two possible base cases. So now how do we rewrite 40 line to 52 without using list slicing? Because list slicing is bad and you shouldn't do it unless you have to. So how do we compare this? So it's quite simple actually. We can just do something like this. Now if a of I is less than b of j, right? Return a of I plus self.merge on a b I plus 1 j, right? Else right, if a is smaller than the b element, then we increment it by 1, else we increment the j element by 1. So this actually takes, line 49 and 51 now takes constant time because this plus is just appending to the list, to this list right here. And on average, this takes constant time. So let's actually test out our merge function before we do approach 2, right? So let's look at our handy example. So our class is get case, so maybe we can do something like this. C go to get case dot merge a b 0 0 print c. So if this is correct, we would expect 1 2 3 4 5 6 7 8 9. So let's see if we did it correctly. Did we? Yes, we have did it correctly. You can see C is printed out to be 1 2 3 4 5 6 7 8 9. Okay, great. So we know that now our merge function works, and our merge function will now take O of n a plus n b time, which is O n in time, and similarly in space as well. Why in space? Because that's how deep the recursion depths must go before we return. Okay, great. So now we can just actually use approach 2. So now approach 2, the overall time complexity in approach 2 is just actually the running time complexity of merge, because line 63 to 68 takes constant time because we're doing direct access to our array C, right? So the bulk of the problem for approach 2 is actually figuring out how to properly implement the merge function, which we have done so up here. So approach 2 will take O of n in time and O of n in space, because merge takes O of n in time, and we're returning an array that's equal to the length of A and B combined. So that's why it also takes O of n in space. Now, this is pretty good. We have improved our time complexity from n log n to just log n. Though our space complexity got a little bit worse, because before we were just log n in space. Now we're O of n in space. So now your interviewer may be saying, can you actually come up with a faster approach? It was good that we sort of the merge, like in merge sort, to combine the arrays, but can we actually use a similar concept when learning about merge sort to actually come up with a faster algorithm? Like, can we maybe use divide and conquer? So now your interviewer has given you the hint of divide and conquer. So you should maybe think of it maybe a logarithmic time complexity. So can we actually devise an algorithm to solve this problem in order k time, sorry, log k time? So final approach, let's move all this junk down. Def, let's call it now your interviewer is like, hey, I want this in order of log k time. And you're thinking to myself, crap, how do I do this? And I'll show you how to do this. We use divide and conquer. But before we actually jump into the algorithm, let's think about the intuition that we can build from approach 1 and approach 2. So let's look, and to do this, we need to look at the definition of what the median is again. The definition of median is that we want a number in the middle of our array such that 50% is smaller and 50% is bigger, where we're able to get this by relying on sorting and using direct access to access the element, because we know the length of the union of the two arrays. So is there a way to do this in log time? And let's think about it. Let's look at A and B again. So the lengths of A and B combined is what? 1, 2, 3, 4, 5, 6, 7, 8, 9. Let's go to 9. And median n is 9 divided by 4, or divided by 2, which is 4. So the median in this case would be 5, right? 0, 1, 2, 3, 4. And that's 5. So the median index is 4. The fourth smallest number in A and B is what the median is, right? Because 0, 1, 2, 3, 4. 5 is the fourth smallest number. And how can we find this? So if you actually think about it, the fourth smallest number must be in the fourth smallest number in A and the fourth smallest number in B. So the fourth smallest number must be in A of 0 to the fourth smallest. Or in B of 0 to the fourth smallest, right? It must be, it's trivial to see that it must be in one of these two sections. So we have already narrowed down our search space. And then what we can do by knowing this fact is compare the middle element in A and the middle element in B between the 0 to the fourth and 0 to the fourth. And let's look at an example, actually. If say for A, we would have to compare the whole array because 4, it's too small, right? So we need to compare the whole array so that it's in the range of 0 to 4. And B, it's 0, 1, 2, 3, 4. We care about these initial elements, right? So the median must be between this range and this range. So let's compare the middle element in here between A and B of these two sections. So the middle element in A is actually 5, right? And the middle element in the 0 to 4th element in B is 4. Right? So A is actually greater than 4. So this must mean that there are at least k elements in A that are greater than b. So we need to actually, so we can throw out all these values because they necessarily must not be our smallest element. So we can actually throw away these three elements in the search space, and then our remaining search space will be 6 and 8, right? And now we compare the middle element of 6 and 8 with 5 again, and we keep doing this until we find our median. So what does this actually look like in code? This is a little bit complicated, but I think once we look at the code and then we revisit the explanation again, it becomes a lot clearer. Okay, so let's see. Again, n is equal to len of a plus len of b, right? If n modulo 2 doesn't equal 0, we can return get case smallest of a, b, 0. The case smallest 0, 0, and modulo 2, right? We can just return the middle number. Else, first two, this one, return the second, right? Because if the total length of the array is we just get the middle element, else we have to take the average. So how do we actually get the case smallest? So this is the hard part. This is where the hard part comes in. Y, J, and K. So I represents the beginning element of A, and J represents the beginning element in B. So initially, they're their zeroth index, right? Because like I said, the case element in A and B must exist between 0 and K. So that's why I initialized it, both of them, to 0. So let's think about this problem a little bit to account for some edge cases. So what if the index of I or J is out of bounds, meaning that there's nothing left to compare in A, or there's nothing left to compare in B, or if say A is empty or B is empty, right? So we can say something like this: if I is equal to length of A, right? That means we're out of bounds for A, or A is empty. Then we know that the answer must be B, because if there's nothing left in A, then the answer must be B, right? So we can return the case element in B. So what this means is that, for example, A is equal to empty and B is equal to 1, 2, 3. Then the case element is just this one, right? Because 3 integer divided by 2 is 1, and J starts at 0, so B of 1 is 2, and that's our median, right? So likewise, now if J is equal to length of B, return A of I plus K. Median must be in B because we have nothing to compare with in A. And likewise, in line 29, this means that the median must be in B because the median must be in A because we have nothing to compare with in A. And what if we have the K equals 0? So that means that we're looking at the first element. So that's just actually min of A of I and B of J. So we get after the 0th element, right? Then that's just like looking at the first element in each of the arrays A and B. So these are our three possible base cases. And we need to now do the partitioning, compare the middle element of 0 to k in A and compare the middle element of 0 to k in B and figure out how to reduce our search space. And we can do this by something like this. So mid1 or mid A index is equal to k plus 1 divided by 2. And mid B index is also equal to k plus 1 divided by 2, right? Because we just care about the beginning or the end, what the case element is, divided by 2. But actually, we need to also consider what happens if, say, one of them is out of bounds. So that's why I'm doing len of A minus I and len of B minus J to account for edge cases so that we don't get values that are outside of our index. And this is where we do the comparison. Mid A is equal to nums, or actually A of I plus index is 1. Mid B is going to be of J plus 1. So this is the middle value in our search space of A and B. And this is where and now we apply the definition. Now we apply the definition of what a median means. So if, let's say mid B is greater than mid A, this means that there are at least k elements in B that are greater than the value of mid A, right? Because if, say, example, say A is equal to 0 da 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 da, da k da 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 da, and right, these are the index. And if mid A is here and mid B is here, then if B is greater than A, right? If B is greater than an A, then everything here is also greater than A, and everything in A here is also greater than A. So the median cannot exist between 0 and mid A, right? It cannot. It must be, we need to check somewhere in here. Does that make sense? Let me say it again. So if mid B is greater than mid A, then there are k elements in that are greater than, at least k elements that are greater than mid A, because we have all the elements from k to mid B that are greater than A, and we have all the elements that are greater than mid A up to k that are greater than mid A as well. So given this condition, we can say something like return get k smallest of I plus mid 1, right? So we just start our search space here. J and k minus, right? Because our case element will be smaller now because we have reduced our search space to between here and here. Else, so now if now we have the other condition. So return k smallest of I j plus index k minus, and now we return this. So now if we look at this, the time and space complexity is log n. Oh, sorry, log k and in time and space, right? Because we're throwing away part of our search space every time we do a recursive call, and we have to do this k times, which is why to get to which one of the base conditions, which is why our time and space complexity is log k. So let's actually test this out to see if it works. Let's look at our handy example. Let's see, print case dot, what is it, approach 3, A and B. So let's get A and B up here. All right, let's hope this works. 5, great, this works. So we get the case element and we get 5. This was really great. So let's see if we add 10 does it still work. 5.5, that is correct. Let's check maybe 1, 2, 3, and if B is empty, does it give us 2? This is also correct. What about 4? Great. 10, 3, yep, that's correct. 19, this is still correct. Let's try 1, 1, 1, 1, 1, 1, 1. This should be 1. This should also be 1. Yeah, this looks like our algorithm is just working as expected. So this is great. We were able to come up with 3 solutions to this problem. The naive n-log n1, a better solution that was linear in time, and now we came up with a log time and space complexity to this solution. Now there are other ways to go about solving this problem as well. So now that you were struggling to solve this problem, your interviewer might now be like, this is pretty good, but can you do this in constant space? A variation would be like, do this in constant space. And you should think to yourself, yeah, you should be able to, but why? Because if you think about this problem, this is actually very similar to binary search, where we're reducing our search space by half every time. And binary search can be implemented iteratively if we just know the bounds of our search space. So for this particular problem, we actually have 4 bounds that we care about: the lower bounding A and the upper bounding A, lower bounding B and upper bounding B. So this can be a challenge to you to implement the case smallest in order 1 space, but also in log time. So that's one variation. And let's say that you're really, really smart and you were able to solve this problem, discuss the time-space trade-off, and come up with the optimal solution that takes log time and order 1 space. Now your interviewers may ask you something like this as a follow-up. So what happens if we cannot fit A and B into RAM? Like, we don't have enough memory to process anything. Like, if you try to load A and B into your computer, it will crash because you don't have memory to it. How will you solve out this problem then? Can you devise an algorithm and talk about the time-space complexity of how to solve this problem if A and B are so large that we can't process it all at once in RAM? So this is a great follow-up for this problem. And overall, I think if you're able to get to approach 3, you should receive some pretty high marks for this problem. And I think the follow-up, if A and B are so large that they can't fit in RAM, if you can think of a solution and discuss it, then that'll be really great. I think that's a really big challenge, and it requires a lot of thinking. So let me know what you guys think, and these are all some pretty interesting problems. And if you have a problem that you have in mind, just post it down in the comments below, and I'll try my best to solve it if I can, that is. Or if you notice that I said something that's wrong or made a mistake in the code, please feel free to correct me, and I'll see you guys next time.